This is lesson 2 in the capacitance topic. This time we're looking at capacitors in circuits and how they behave when they're in series and in parallel to another. First off, we'll look at capacitors in parallel. So here I've got a capacitor C1, capacitor C2, and they're connected in parallel with each other. And then there might be some battery or power supply that's connected to with some voltage across them. They each have their own charge Q on them. And what we can actually do is we can think about this as a single capacitor. So what we want to think about is how does these two capacitors in parallel behave if it was just one capacitor. We do this with resistors. We think about resistor 1 and resistor 2 in parallel with each other. What would the total resistance of that be? How can we consider it as one single resistor? We can do the same with capacitors. We can work out the total capacitance of this. So what we're going to do, we're going to imagine these two in parallel as one single capacitor. And you might be able to see that we've now got a total capacitance C, a total charge of Q, and the voltage across it is still V. Notice what's happened here to the charge on each plate of the capacitor. So we're going to come to the potential difference, the charge, and the capacitance. Potential difference, when it's in parallel, is the same on each capacitor. So each capacitor there has the same potential difference. V1 equals V2. The same potential difference on both. The charge is conserved in any circuit. So here we've got charge being conserved, which leaves us with the total charge of both capacitors being the sum of both of them. So the total charge on capacitors is Q1 plus Q2. And finally, the total capacitance is C1 plus C2. The total capacitance, if we imagine it as one combined capacitor, is just the capacitance of each one added together. In parallel, it's actually fairly straightforward. So let's look at a worked example of this. I've got to calculate the total capacitance when a 3 microfarad capacitor is connected in parallel with a 2 microfarad capacitor. It would look like this. So that's my drawing of it. This is one of your Isaac physics questions, by the way. In parallel, we have this equation for capacitance. Total capacitance equals C1 plus C2. So I'm going to have 2 microfarads plus 3 microfarads equals a total capacitance of 5 microfarads. Very straightforward. Let's have a look now at capacitors in series. When I've got capacitors in series, it's a little bit more complicated. So looking here, I've got capacitor with a capacitance of C1, another capacitor with a capacitance of C2, and Q1 on this plate, or on this capacitor, Q2 on this capacitor, and V1 and V2 on both capacitors. Let's now consider this again as a single capacitor. And now let's try and describe the potential difference, the charge, and the capacitance on this single capacitor that is sort of modelling what these two would look like, how they would act in a circuit. So the potential difference is different on different capacitors. We get a different potential difference on different capacitors. It depends on what the capacitance is for each one. The total potential difference is equal to V1 plus V2. Potential difference of the first one plus the potential difference of the second will equal the total potential difference. And that will be the potential difference of that power supply if there's nothing else in the circuit. The charge will be the same on each capacitor. The charge is the same on each capacitor. So we can say that Q1 will be equal to Q2. And we'll talk about why that is in a second. And for capacitance, finally, in series, we are left with 1 over C, so the total, C is the total capacitance, 1 over the total capacitance is equal to 1 over C1 plus 1 over C2. This looks very similar to the equation for resistance in a parallel circuit, but this is capacitance in a series circuit. We'll look at those at the very end of the lesson and how they compare. Let's practice this now in an example. So I've got to calculate the total capacitance when a 3 microfarad capacitor is connected in series with a 2 microfarad capacitor. Again, this is one of your Isaac physics questions. This is a sketch of what it would look like. In series, I calculate capacitance with this equation. And I'm therefore going to get 1 over the total capacitance C equals 1 over 3 plus 1 over 2. Therefore, 1 over C equals 5 over 6. Inverse that to get C is equal to 6 over 5 or 1.2 microfarads. Because I had micros before, I'll have microfarads after. To think about why capacitance acts like this in series, let's imagine this diagram here. So I've got 3 capacitors all connected in series. And this little blue dot here is an electron. So consider the electron arriving at the bottom of this plate here, C3. Now when the electron arrives at the bottom of that plate, this plate now gains a charge of -1 because it's got an extra electron on it. This electron, having joined this plate, is going to be repelling an electron on the opposite plate away from it. If one negative charge arrives here, it's going to be repelling another negative charge away from this plate. So then I'm going to get an electron being repelled away from that plate, which leaves a slight positive charge on this top plate here. So this top plate here is left with a positive charge of +1. This electron that has arrived at the bottom of plate C2 gives the bottom of plate C2 a negative -1 charge. This charge will then repel another positive charge from the top of plate C2. And as it repels an electron away from that top of C2, it will leave it with a positive charge. As an electron comes to the bottom of plate C1, it's again going to repel another electron away from the top of plate C1. And that will then leave that with an overall positive charge there as that electron moves away. What you can notice is that we're going to look at these 4 plates here in the middle, the top of C3, the 2 C2 plates and the bottom of C1, they all sort of cancel each other out really. So here with our capacitors in series, each capacitor has got the same charge. And we just looked at that in the previous slide as to why that is. Each capacitor has the same charge. Now there's no actual circuit connection between plate A and plate B. It's just a gap. A capacitor is just a metal plate and a metal plate with a gap in between it. So there's no actual circuit connection. So what we've got is charge on A being equal to the charge on B. And that is also equal to the charge on all the other plates that would be in between. Basically, plate A and plate B form one large capacitor. These middle plates here all basically cancel each other out. So that what we can do is we can effectively just think about plate A and plate B as being one capacitor, just with a big gap in between them. And when you increase the spacing inside a capacitor, increasing spacing decreases capacitance, which is why capacitors in series make the total capacitance go down. So it can sort of be thought of as one large capacitor. Looking at combining capacitors now in series and in parallel, we've got a 6 microfarad capacitor connected in parallel with a 4 microfarad capacitor, and then that is then connected in series with a 20 microfarad capacitor. What's the total capacitance? Well, this is going to be my diagram. I've got 6, 4 and 20. What I'm going to do first of all is I'm going to think about this as one capacitor. So I'm going to work out the total capacitance of this parallel section, and then I'll treat that sort of single capacitor and that single capacitor as being in series. So first of all, let's do the parallel bit. We know the equation for capacitance in parallel is this, and therefore 6 plus 4 gives me a total capacitance of the parallel section as 10 microfarads. Then thinking about having a series circuit, and I would then have a 10 microfarad capacitor here and a 20 microfarad capacitor here. Using the equation for capacitance in series, I would have 1 over C, 1 over the total capacitance, is equal to 1 over 10, which is this bit here, plus 1 over 20, which is this bit here, would give me 3 over 20. Then I need to inverse that to get C equals 20 over 3, or 6.7 microfarads. So finally, to summarise, we can think about series and parallel circuits and compare resistance and capacitance. In resistance, to calculate resistance, in series, we just add the resistances together, and in parallel, we do 1 over R equals 1 over R1 plus 1 over R2, etc., etc. It's the other way around for capacitance. So in capacitance for series, we use this equation. In capacitance in parallel, we use this equation.